So like you can change the slot in your schedule permanently. So day 5 I will always take the second class. So okay, recording has started, so let's begin. Now infinite slopes, as I have already told you, like these are those kind of slopes which cannot be analyzed totally, okay, from like top to bottom. So at any point of time, if you have any problem with the audio or the viewing, you can please let me know. So now for stability of infinite slopes, we will be discussing an infinite slope where we cannot analyze the whole slope at a time. Finite slopes were like this type of slopes where we could analyze the whole slope at one time. Okay, so in infinite slope, you cannot do that. In infinite slope, you cannot like uh, you cannot analyze the whole slope at a particular time. You have to analyze a part of the slope. That means if this is an infinite slope, you cannot analyze it from here to here at a time. So you have to take one particular section, suppose from here to here, and then you have to analyze this part. Okay, and whatever value you get, you take it as the final value for your slope. Am I clear? So now let's begin. So generally, uh, the forces that disturb the slopes, okay, the forces that disturbs the slopes are generally the gravity force, which which is like the self weight of the soil of the slope. Okay, self weight of the soil of the slope, which can give the disturbance. The weight itself can be the disturbing force. Then seepage, that means water passing through the soil, can give the disturbing force. And number third can be earthquake. Okay, so these are the disturbing forces. Okay, and also one thing you need to understand is that the slopes can be natural. The slopes which are found, okay, can be natural or can also be man-made. The slopes that are found can be natural or can be man-made. And can you give me some example of man-made slopes? Anyone in the chat box? Give me an example of man-made slopes. Man-made slope. Give me an example. Dams. Then, yes, you are correct. Slope, yes. Stairs, like we are talking about soil point of view. So stairs will not be the like obviously stairs is a slope, but we are talking from the point of view of soil. So stairs will not be the proper answer. And bridge, yeah, bridge. How like bridge? You see, we are talking from the soil point of view. Slopes made from soil. So like stairs, bridges, they are not related to soil. They are not made out of soil, isn't it? So, like even if they have slopes, I am not asking about that. I am asking about the slopes which is built from soil. So, yeah, perfect answers, the most appropriate answers in this case. Okay, levees. Okay, yeah. So the perfect answers will be for man-made slopes. We can say like arch dam. I'm glad for those who have given the appropriate answers, and I feel glad when you all respond. 10 dams, embankments. Okay, so yeah, man-made slopes are like that. So now, when we analyze the slope, okay, so let me take a new screen. When we analyze a slope, okay, for the forces, we always analyze it for the limiting equilibrium. Limiting equilibrium. Otherwise, it is not possible to analyze it. Just remember, suppose for simply supported beams or trusses, when you did the analysis, suppose for trusses, when you did the analysis, or simply supported beams, when you did the analysis like this, simply supported beams. So when you did it, you took some equilibrium condition, right? You took some equilibrium condition like for forces and all, isn't it? Equilibrium condition where the resisting force was equal to the applied force. So we have to take the equilibrium condition in case of the slope also in order to analyze it. So for slopes, the equilibrium condition when we take it, it will be for the shear criteria. Okay, because the main force that is disturbing the slope or which is making the soil tear off and slide down is the shear force. Okay, so for limiting equilibrium condition, the the way in which we have to write it is applied force, which is shear stress, should be equal to shear strength. Okay, and also for factor of safety, you should remember that we have already discussed factor of safety is equal to maximum resistance by mobilized resistance. Factor of safety we have already discussed, resisting moment by disturbing moment, like that. Maximum resistance means what? The capacity. Maximum resistance means the capacity of resisting, how much it can resist. And the mobilized resistance is what it is actually resisting at that particular time. That is the mobilized resistance. Okay, should I give you a revision about the mobilized strength once again, so that it would be better for you? If yes, then I can just take 2-3 minutes and I can just give a revision, or else I can proceed. What do you want? You can tell. Yes, hills are slopes, obviously. Yes. Do you want me to repeat the mobilized part, or it's fine? I can proceed. Why means you are telling me to proceed, or you are telling me to repeat it? Okay, okay, okay. So, you see, let me take a new screen. So you let me give you an example. You are, suppose this is you. You have a capacity to take 100 kg. You can take. Okay, you can like carry. Okay, this is your what maximum what resistance that it can give. So this is like maximum resistance, or like we can say maximum capacity, or maximum we can say strength. Okay, so this is like you can take 100 kg. Okay, you can take it, you can like lift 100 kg. Okay, now in the second situation, like uh, in the second situation, like 50 kg you are lifting, like 50 kg load is on you. Okay, so you have 100 kg capacity, which is the maximum resistance. See, 100 kg your capacity means 100 kg is the resistance you can give. You can give a maximum of 100 kg resistance. So you can take a load of 100 kg. So 100 kg is your capacity, 100 kg is your strength. All are the same meaning. All are the same meaning. Then someone has to given you 50 kg load to pick up. So out of your capacity, you will use only 50 kg strength, only 50 kg of your strength. That means what? In simple words, not in simple words actually, like if I elaborate it, what you will do is you will mobilize only 50 kg of your capacity. Okay, and whatever you have mobilized is equal to the applied load, isn't it? 50 kg is the applied load on you right now. So applied load is equal to the mobilized strength. So what if you are given a load of 50 kilo to pick up, out of your strength you will mobilize only 50 kilo of your strength. Why to utilize 100 kilo capacity is useless. So whatever you mobilize is always equal to the applied force. So now in the previous lectures, now if you relate it to your previous lectures, we have discussed that factor of safety is equal to the resisting moment, resisting moment by disturbing moment, isn't it? We have discussed it in your previous class, disturbing moment. So resisting moment means what? It's the same as the capacity. How much the slope can resist. That is the capacity. How much the slope can resist. And disturbing moments means what? How much it has been applied. And it will be same as the mobilized value. That's why right now, if I try to write the definition and in another way, we can write in the same language. We can write maximum resistance. Resisting moment means what? In case of slopes, since we are talking about moments, because in slopes we will generally go with moments, because moments are the one that are like making the failure. So maximum resistance and resisting moment is the same thing. Okay, your total capacity. Okay, so this one same meaning. And next in the denominator is written mobilized resistance. And whatever you mobilize, whatever the slope, in this case whatever it will be mobilizing, it is same as the applied force. Okay, so disturbing force is equal to the mobilized force. 50 kg you are being given, it is like disturbing you, right? So you are mobilizing 50 kg of your strength. So that's why this definition that we have discussed in the previous class, resisting moment by disturbing moment, can also be written as maximum resistance by mobilized resistance. Are you clear? Step Y. Step Y. I need more of Y's. So that's why, like, don't get confused. It's the same thing. Okay, definitions is the same thing. Sometimes you may get the second one, like this one. Sometimes you may get this formula. Sometimes you may get this formula. Do not get confused. It's the same. At the top, you always write the capacity of the slope. Okay, and at the bottom, you always write the mobilized value. Means whatever load is being applied. So that's all. So now let us now go deep into the infinite slope, to go seriously into the analysis of the infinite slope. So let us draw an infinite slope. So like it has to look like an infinite slope. So I am drawing it like this. Okay, so I will cut out a little bit portion from here. Okay, and let us consider that the width of this portion is B. Okay, and the depth of the portion that I am cutting out is Z. And let us assume that the slope is beta. Who will be taking your next class? May I know? Who will take? Okay, okay. I will leave at around 11, 10:50, so that like you get some rest. Okay, 10 minutes, 10, 15 minutes. I don't like so much of constant screen time. I'm being honest. I don't like so much of constant screen time. You also need some rest. So I will stop by 10:50. So now, if this is beta, if this is beta, so if this is also beta, then this will be what? B cos beta. I am just using some trigonometry. So there are some assumptions that you need to take while doing the analysis. Number one is that it is a 2D case. That means there is unit width. Okay, and there are two other conditions like C phi is constant and C phase forces, the water moving through the soil, the force due to the water moving through the soil can be found out. If it is needed to be found out, the force due to the water, then we have to use flow net for that. So that will be dealt on later. That is a little bit higher level, not for your like BTech. Okay, so let us first let's go with this assumption itself. Okay, whatever you require at your BTech level, we will restrict ourselves to that. Okay, so first you need to know that it is a 2D case, and it is for unit width. Okay, so width is unit. So can you please calculate the volume of this section that I have cut? What will be the volume? Volume will be area into thickness, and thickness I have already taken, it is unit width. Okay, so it is 1. What is the area? Can you please calculate? And um, you cannot, might not be able to type it in the chat box, the area. So yes, I will do it. I'll do it. If it would have been able to like type it in the chat box, I would have asked you to type it, calculate it, and type it. So this is a parallelogram, isn't it? So A, B, C, D. If I consider A, B, C, D. Okay. So I need volume first. Okay, volume. So for that, mainly I need the area. Area I get. Area into 1 is the volume. So it is half into sum of the two parallel sides. It is a parallelogram. So sum of the two parallel sides into shortest distance between them. Shortest distance between them. So it will be half into sum of the two parallel sides is just what into twice z. Z plus z. So this is also z. Sum of the two parallel sides twice z into it will be b cos beta, shortest distance. So ultimately we can write volume is equal to zb cos beta. 2 gets cancelled. Now I have got the volume. So what is the weight? I have told you that weight is a disturbing force. So we need the weight. So our main purpose of calculating the volume was actually to find out the weight. So let us consider that the unit weight of the soil is gamma. Okay, so if unit weight of the soil is gamma, then the total weight will be gamma zb cos beta. Am I clear? Am I clear? Am I clear till now? Okay, so now gamma z b cos beta. So this weight will act perpendicularly. Okay, this weight will act perpendicularly. So if this is the weight, let me consider this one, gamma z b cos beta. What is the stress due to the weight? What will be the stress due to this weight? Stress is equal to what? Load by area. Okay, W by area, isn't it? So what is the area in this case? This cross-sectional area, isn't it? This cross-sectional area. This cross-sectional area. So you cannot see this cross-sectional area because it is a 2D case. So what will be the cross-sectional area generally? It is the length into thickness. So it will be what? Area is B into 1, length into thickness. Okay, so and this W is what? Gamma Z B cos beta. So ultimately the stress due to the weight is gamma Z cos beta. So ultimately if I modify it, I can write it like this: sigma, where sigma is equal to gamma Z because gamma Z cos beta. Okay, so this stress will have two components like this and one like this. This will be normal and this will be the shear component. Okay, so shear component I will write it like this because ultimately this is the only force that is disturbing. This is the only force that is failing the soil. Is there any other load? No, there is no load. Only the weight is there. So that is the only soil that the only load that can fail it. So what are the components of that load? So these are the normal component and the parallel component. Parallel component is the shear force and the normal component is sigma n. Okay, so if the slope is beta, if this is beta, so then this also becomes beta. If this is beta, then this also becomes beta. So this gamma n will be sigma cos beta. It's like resolution of the force, and tau will be sigma sine beta. So if I try to elaborate it, sigma n will be sigma cos beta. So gamma z cos beta into cos beta. So ultimately gamma z cos square beta and tau it will be gamma z cos beta sin beta. So these are the values that we will get. Okay, so this is the shear force and the normal force that is acting on this soil. Okay, so now after this, the steps that we will be doing, like it will not be good enough to like complete it today because then it will be like uh, I want to complete the next steps. Like after this, I will complete this analysis at a single stretch. Okay, so I don't want to like leave it incomplete today itself. It will need some time. So like let us stop it here today. You please go through it till here. Okay, just be clear with how we have got the um, equations. Please be clear with how we have derived the equations. That is very, very important. Okay, once you are clear with the equations, then remaining steps becomes easier to understand because then you don't get confused with the terms. Okay, otherwise like you might be in a dilemma like where this term has come, where has this term come. Please be very, make yourself familiar with these terms. Tau formula, sigma n, sigma formula. Please make yourself familiar. This volume also, please make yourself familiar. If possible, write it once more. Okay. And as I do, as like I follow one theory which is like revision is more important than studying. Okay, if studying is important, revision is twice as important. Without revision, studying fails. So give twice the importance to revision. Okay, so please do revise it. Okay, and be comfortable with these terms, and then we can finish the whole analysis of the infinite slope at a single stretch in the next class. So thank you very much for your patience listening and thank you very much for your time.
Thank you, sir.
Thank you. Thank you all. Thank you all.